All right, we'll go ahead and get started. Let me share my screen and we will be underway for today. Okay, welcome back. This is our third webinar, week 3 of our qualitative practice exam book launch. Each of these webinar series, we are solving about 4 or 5 problems from the new book. Again, if you've been paying attention, you know that the P exam seems to be shifting more and more and more qualitative, meaning that it doesn't matter how good you can use this to solve problems and maybe even answer questions that you're not that familiar with, doesn't matter, right? We need to be familiar with theory. We need to be related with qualitative relationships, right? If I change this variable, what happens to this variable? We need to be familiar with using the correct machine or apparatus for the given application, all that good stuff, right? A lot of this comes from industry experience, right? The PE exam, even though most states are now decoupled, you can take it before you have your 4 years of experience. The PE exam, it's still really meant to also evaluate your career experience. So keep that in mind. But it's okay. They test on every part of the industry, whether or not you're in it. You could be in the MEP industry, focused on building design, and then having to answer questions on overhead high voltage transmission lines, right? So a lot of the stuff we can teach. And the good news, a lot of the stuff is I can show you easy ways to solve these problems by looking at the different relationships in the formula. So a lot of tricks there. I typically call those quantitative with numbers, problems disguised as qualitative problems. So I would say a good majority of the qualitative questions of the P exam, as long as you're familiar with the different formulas that we can pull from, that we would normally use to calculate values, we can investigate those formulas to see how the different relationships change when we change specific conditions. So who here attended the first webinar? Give me a 1 in the chat. Who here was here live on January 9th, 2025. Good, lots of ones in the chat. If you weren't here on January 9th, did you catch the recording? Anyone catch the recording of that one on YouTube? Good. How about who here was also here last week, January 16th? Give me a 2 in the chat. If you were here last Thursday for week 2 of qualitative questions. Good, lots of 2s. And great. Who here is tuning in for the first time? Give me a 3. This is your first qualitative webinar for the Power PE exam. Give me a 3 if you missed any of the other 2. Okay, so those of you that hit number 3 in the chat, good news is the recordings of each of these are on YouTube, and of course I'll make this one available as well. So today's January 23rd. We're on week 3. We'll be doing one more of these next Thursday on January 30th. And that'll wrap up this 4-week seminar series. Now, what's this all about, right? This is promoting our brand new book called Mastering the PE Exam, 100 Qualitative Practice Problems for the Electrical Power PE Exam. It's our third book. It's amazing. Nothing like this exists on the market. Again, the PE exam for power specifically continues to trend more and more qualitative. And there are no qualitative only resources or study aids. So instead of designing this like a typical practice exam, like our technical study guide or our AIT practice exams, and I've got copies of those over both of my shoulders, um, I designed this to be used in tandem with our online class. So there's 100 problems total, almost 300 pages. And the way it works, it's broken off into about 10 to 13 questions. Again, following the schedule of our live class. So the first chapter is circuit analysis, second chapter is transformers, third chapter, rotating machines, fourth chapter is devices in power electronics, so on and so forth. And you'll also notice in this book, the solutions follow each chapter. That way you're not digging at the very back of the book. So when you get a copy of this, I really recommend not using it like a practice exam. There's 100 problems instead of 80. I really recommend learning those qualitative aspects at the appropriate time for you. If you're in our online class, I would use them as additional homework problems for class. If you're not in our online class, then as you learn transformers, hey, work the transformer qualitative problems. As you learn protection, work the protection problems. That way you're getting exposed to these relationships that have all at once when it's hard to remember. You can get exposed to each specific subject when you're learning that subject. Now, during the book launch, I do have it currently priced on Amazon.com at the lowest price that Amazon will let me list it for It's $20.50. I earn exactly $0 in royalties at this price. Seriously, I'm selling it at the direct cost. Why? Well, we've got a ton of books. Really just want to get it in as many hands as possible. So if you already have an Amazon Prime account, you can get this shipped to your doorstep in about 2 days. Now, in the next month or so, I will be raising the price to probably about $39, which is typically the market price for a PE practice exam. Easiest way to find this book and our other two books on Amazon.com is just search for my name. If you type in Zach Stone followed by PE, it'll pull up my author profile. You'll see all the books. Easiest way to find it. Funnily enough, if you search just Zach Stone, there's an MTV comedy show from like 10 years ago that pops up. So watch out for that. That's not going to help you very much for the PE exam. Okay, so where did we leave off? There's a 5% sale, said Crystal. Good. So right now it's actually listed for $19.48. Yeah, guarantee it'll never be that low again. So if you're looking for a copy, snag it. Those of you that are enrolled in our online class, you know that you already have access to the early release version of all the individual chapters. You got about 70% of the book. And again, in about a month or so, I'll be releasing the digitally published PDF in its entirety to our online students. So if you're already enrolled in class, you have just about all the problems in this book already. Anytime we publish new material, it's always included with both of our paid enrollment plans at no additional cost. All right, so where do we leave off? I think we are on problem 9, applications. And for me, that's on page 24. Yeah, we worked through this last time current curve problem last week, looking at the TCC curves for fuses, thermal mag breakers, electronic trip breakers, and protection relays. So now we're going to be starting with applications. All right, number 9. Select the statement below that is most correct regarding the difference between grounding and bonding. A, grounding ensures all metal parts are the same electrical potential, while bonding provides a path for electrical current to return to the source during a fault. B, grounding connects the electrical system to Earth, while bonding creates a continuous electrical connection between metal parts to ensure they remain at the same potential. C, grounding only applies to electrical panels, whereas bonding is used exclusively for wiring enclosures. Or D, bonding connects a system directly to the Earth, while grounding connects metal parts together to equalize their potential. A, B, C, or D. What do we think? Grounding and bonding, and even sometimes earthing, subtle differences, right? These terms pretty much come from the National Electrical Code, and they're commonly mixed up. What do we think? Let's see. I'm seeing great, just about all B's in the chat. You guys cheating? Are you guys existing students that have already worked this problem? That's great. The answer is, in fact, B. This is a tough one. These vocabulary words are pretty close, and the answer choices are pretty close too. So here's the answer. B, grounding connects the electrical system, keyword, the system, to Earth. What's the easiest way to think about that? I think grounding, I think where my feet are, right? My feet connect me to the Earth. So when we ground the system, we're connecting the system to Earth. It's like the feet or the legs of our electrical system. And then bonding creates a continuous electrical connection, keyword, between metal parts to ensure that they remain at the same potential. All right, let's investigate these terms a little bit further. Again, these are often misunderstood. You can buy books that, are hundreds of pages specifically just discussing the different examples and the differences between grounding and bonding. So grounding, when we look at a service transformer, or when we look at a large enough transformer that's feeding, a big feeder bank, the way that transformer is grounded, that dictates the system grounding. So grounding, look, if here's, say, our service transformer or a big enough transformer in the distribution panel, maybe we're feeding a whole separate building or something like that. Here's our grounding. In this case, I'm just showing you a Y-connected secondary transformer with this is a solid grounded, right? Could have put a resistor in there and showed it neutral grounded resistor too. Either way works. So grounding is the intentional connection to Earth, typically performed, yeah, at the service transformer by means of a Y secondary. Most common examples of grounding is solid ground. We're just using a conductor or high resistance ground, right? Industry term for that, NGR for a neutral grounding resistor. Only difference between a resistance ground and a solid ground is I would stick a big resistor in between my neutral and my ground to limit that fault current according to Ohm's law. Another good qualitative relationship. So what's the purpose? Why do we want to create this intentional connection to Earth at the service transformer? So the main purpose is we want to be able to safely dissipate excess electrical energy. So when we have fault currents, right, ground faults, or lightning strikes that induce really large, high frequency voltage transient and current spikes, when our transformer secondary is grounded, it provides a place for these disturbances to go, right? It's kind of like a heat sink, sort of. In addition to that, the second main purpose is if I have a ground fault and I want to be able to measure and detect ground faults, and if I want to be able to have a ground fault protection scheme so that I can operate the service transformer over current protection devices, well, then I need a connection back to the transformer. I need to provide a path to ground for ground fault current to flow through the bonded connections that we're going to talk about here in order so that we can, okay, now I can stick a current transformer on that connection from ground back to our source. Now I can connect a CT on that connection. I can connect that to a relay. Now I can monitor, measure, and detect the presence of any ground fault current. And then once I have that information, I can set up a protection scheme to trip at a specified ground fault amount. So it's kind of counterintuitive, right? If we want to be able to trip for ground faults, well, then we need to provide a path for those ground faults to flow. Otherwise, like a ground fault on an ungrounded system, who is here? And we talked about this at the very end of last night's class. If I have an ungrounded system, so this Y solidly grounded secondary, if there was no connection to ground, what happens if I have a ground fault? Anything happen? If it's ungrounded, what happens? Nothing. The system remains energized even with a ground fault. So if we want to detect ground faults, then we need to provide a closed loop, a continuous circuit, so that they can flow. Otherwise, if it's ungrounded, then technically I have an open circuit to ground. And even with a ground fault, there's no ground fault current. Make sense? Yeah, so these numbers are a little bit different than the actual book numbers. What I did is I just went in order, number one from each subject, then number two from each subject, et cetera, et cetera. In the book, the first 10 or 11 or so are circuit analysis, then the next chapter is transformers, et cetera, et cetera. All right, any questions on grounding before we talk about bonding? I find that most of us are familiar with once we realize, okay, yeah, grounding, that's at the service transformer. Most of us realize the main purpose of that is providing a path to ground fault. But the other purpose is really here. What happens if I have a lightning strike? I don't want those transients bouncing all around my system, wreaking havoc, especially on my insulation. I want a place for them to, I want a place for them to go. Sure. Sam said, can you explain the applications where we use a high resistive ground versus a solid ground? Yeah, and Sam, we talked about this last night in Transformers class, but basically Ohm's law, right? V equals IZ. If I set that equal to the current, I equals V over Z. This solid conductor, if I erase my ground symbol there, that solid conductor, it has a little bit of impedance, right? Whatever the effective impedance is of this conductor, but it's pretty small. Now, if I stick an impedance here or a resistance here, what happens? Increasing the resistive path of my ground fault current or when my ground fault flows. Sam, what happens if this is a great qualitative question, by the way. What happens if I increase the impedance? What happens to the ground fault current? Z is in the denominator of this ratio for Ohm's law. So that means if the denominator, the bottom of the fraction, gets bigger, ground fault current is going to decrease directly, or I would say ground fault, we can say will decrease directly proportional to increases in impedance, or I can say current is inversely proportional to impedance. So what it does is it lets us limit the worst case ground fault current. If I have a solid conductor, the maximum amount of ground fault current is going to flow during ground fault. With a neutral grounding resistor, if I say, I want to limit the ground fault current to a maximum of 3 amps, well, using the system phase voltage and that value of the worst case ground fault current, I can size my neutral grounding resistor to set that maximum limit threshold of how much ground fault current can occur. All right, so how about bonding? What's bonding? Who here has ever swapped out a receptacle at your house, maybe a new light switch? Who here's done any minor wiring? You're getting your hands on the wire nuts, making sure the power's off, all that good stuff. Yeah. So anytime we land, maybe you replaced the ceiling fan in your office, like I did. Anytime you've got that bare metal grounding, equipment grounding conductor, and you land it on the exposed metal parts, that's bonding. Bonding, bonding, again, it's an intentional electrical connection between metal conductive parts such as metal conduit, metal junction boxes, metal enclosures that typically aren't intended to carry current to ensure that they all remain at the same potential. Great example of this, my washing machine in my house. It's a metal enclosure. What happens if one of my wires accidentally comes in contact with that metal enclosure? Maybe my dryer, I've got a really big blanket in there and it's flopping around and a lot of vibrations. And the wire is just sitting there running on on the lip of part of that metal case. It rubs the wire bare so that the insulation breaks. And now the conductive parts of that metal is directly touching with the metal part of the case. What happens if I come by and I go, oh, laundry's done, and I touch the case if it's not bonded? Well, if I touch that case and the case, which is metal, metal conducts electricity, but the metal case or the metal enclosure, it's not designed or intended to carry current, right? An accident's happening. Well, now that I touch it, I'm now part of that electrical circuit, right? Dangerous. So we create an intentional electrical connection to any parts that are metal in our equipment that are not designed to be current carrying conductors. So that if a ground fault happens, well, we now have a low impedance path for that connection. And then we combined bonding with grounding. So for example, if I bond my washing machine or my clothes dryer, which it is, right? If that connection occurs, right, a lot of vibration occurs, the wire gets rubbed raw. Now the metal conductor of the wire is directly touching the metal case. Well, if it's bonded, it's no big deal because now that metal case is already directly connected through the equipment ground conductor all the way back to my panel in my garage where my breakers are. And my panel that's fed by the service transformer is grounded. So now I have a closed electrical circuit from my washing machine or my dryer back to my power supply. And what's going to happen the second that rubbing occurs and the wire touches the metal case, because it's going all the way back to my transformer, my breaker is going to trip. It's going to sense that high fault current. It's going to trip right away. So we typically use grounding and bonding in tandem to protect us, the humans, from ground fault current. Does that make sense? Let's see, primary purpose of bonding. Here we go. Yeah, minimize the risk of electric shock by creating a path for current to return to the power source during ground faults, ensuring the overcurrent protection devices activates and de-energizes the circuit. We're giving the system a low impedance path back to the panel or the breaker. That way, if a ground fault does happen and a human touches it, the human doesn't become that path back to the panel. Makes sense. Even if I touch it, technically I'm still part of that circuit if there's a ground fault. But hey, I got skin, you know, we're what, 70% water. I've got bones, I've got organs. My internal resistance, if I touch it, it's way higher than a bare copper conductor going back to the panel. So it's always going to go back on that conductor instead. All right, any questions? What do we got? Yeah, like equipment grounding, said Daniel. Yeah, you betcha. Um, let's see. Bailey said, should the ground be closest to the equipment operating, if not necessarily a service transfer? Sure. Yeah, especially when you have a big transformer. Jessica said, if something is bonded, does that mean it's also grounded? Or would you ever have something ungrounded but bonded? I don't really think so. I'm sure there's really old, outdated installations there. You know, I've worked around large electrical plants that were medium voltage and ungrounded systems. But in general, your bonding and your grounding work in tandem. You can th kind of think of your grounding as like the final boss of bonding. But instead of connecting to just the metal parts that aren't intended to be current carrying conductors, you're landing it right on the neutral. And another thing we can visualize is, in this transformer, if it's a big transformer, I've got some kind of big metal enclosure, right? Whether I'm in an electrical room, whether it's pad mounted, whether it's a pole mounted transformer, but I'm going to have this is the enclosure. I'm going to have the enclosure is also going to be bonded with an equipment grounding conductor to make sure that, oh, if I have somehow a fault, right? If maybe this phase comes in contact with my enclosure, I want that ground fault to come all the way back. Yeah, Addison said equipment on ships are not bonded. Oh, they are bonded, but they are ungrounded typically. Yeah, they're ungrounded because they're floating in water. Other subtle applications of bonding too, when we talk about ensure that they all remain at the same electrical potential. What's electrical potential mean? If you're not sure, what do we call a voltage transformer for protection? We call it a PT for potential transformer. Yeah, electrical potential is voltage. Great job, Michael. So when I bond things together, is it possible for them to be at different voltage levels if they're bonded, or essentially putting them in parallel? I have two metal enclosures that are not bonded and we have current running in there. I could have eddy currents induced in them, hysteresis induced in them. So if I took my meter and I checked one case to ground and it's not bonded, and I checked the other case to ground and it's not bonded, that we could have some voltage there, a couple of volts, right? If I bond them together, and that difference, there maybe this is 3 volts, maybe that's 5. When I bond them together, well, now they're pretty much in parallel. So they're going to be at the same potential. It's a different potential. Really helpful in sensitive electronics. So back to that maritime example, like Addison said, equipment on ships are bonded but not ungrounded. So yeah, imagine all of your sensitive ships navigation systems, its instrument panel, all that kind of stuff. If all of this equipment's not bonded, remember when current flows, it creates a magnetic field. And that magnetic field is going to induce voltage and current in anything metal nearby. No different than how transformers induce voltage and current from primary to secondary winding. No different from how induction motors induce voltage and current from the stator to the rotor. A conductor by itself carrying power, it's doing that all the time, but it's typically minor enough that it doesn't cause any problems. Well, if I have really sensitive electronics and instrumentation, then that little bit of interference can create inaccurate measurements. And now I'm steering my submarine all backwards. So we also want to bond everything to help eliminate that. Think of like static electricity almost. All right, that's number 9, applications. Let's take a look at number 10, back to circuit analysis. Now, who was here for webinar 1? This is very similar to the first problem we did on circuit analysis. All right, number 10 says 3 identical complex single-phase impedance loads are Y connected to make a complex 3-phase load. Assuming balanced conditions, select the answer below that describes what would happen if the same load was delta connected instead. First of all, if I have a balanced 3-phase load, what does that mean? If I have a Y connected or a delta connected load and it's balanced, what does that immediately tell us? What's the relationship between the impedance and all 3 phases of either the Y connected load or the delta connected load? They're the same. Yeah, Samuel said all loads are equal. So this is saying if I've got a balanced Y load, what happens if I take those same 3 individual impedances that are currently Y connected, if I undo the connection type, and I reconnect them in a triangle. I reconnect them in a delta connection. What's going to happen? Assuming it's connected to the same power supply. A, the load would draw the same amount of apparent power. B, the load would draw 3 times more apparent power. C, the load would draw 1.73 times more apparent power. Of course, 1.73 is what? This is the square root of 3. Or D, the load would draw 1.73 times less apparent power. What do we think? A, B, C, or D? All right, I'm seeing about a mix between A's and B. Anyone else? Don't be shy. Yeah, I'm seeing a mix of A's and B's. All right, here we go. The answer is B. The load's going to draw 3 times more apparent power. How do you figure? So I have a Y-connected load. So whatever this complex impedance is, it's the same in each phase. I break apart the connection type, so it's no longer Y connected. I take the same 3 equal impedances, and now I connect them in a delta configuration. So the easiest way to think about this is we're being asked about what's the relationship with apparent power. Here's our formula for 3-phase apparent power. It's a square root 3 times the magnitude of the line voltage, the magnitude of the line current. When I look down here, assuming there's no change in the voltage, right? Problem didn't mention anything about that. So we assume the same 3-phase power supply. Has anything changed between the line voltage? Let's say this is maybe plus V A B minus. And this is our A and B. Has anything changed when I go from Y to delta if I haven't changed my connection, or excuse me, if I haven't changed the power supply? No change in the line voltage, right? I still have the same A to B line voltage. Instead, what has changed? If the line voltage has not changed, is there a different voltage that might have changed? I don't know why it keeps going. Blue. No change to impedance. Careful, Charles. We're taking the same impedance, but now we're just delta connecting it. How about what's the phase voltage of my Y connection? Phase voltage of my, here's the A phase impedance. I've got A to neutral, right? Smaller than my line voltage. What's the phase voltage at my delta? Now the phase voltage is equal to the line voltage because it's delta connected, right? Very interesting. No change in the actual impedance values, but now the phase voltage directly across the impedance has changed. When we go to the delta connection, it's increased. Technically, it's increased by the square root of 3. Let's see what that does to the power. Easiest way to calculate power, look, we're assuming the line voltage is constant. So if this was a quantitative problem where we know the numbers, I would assume I've got that information like 480 or 208 volts three phase. Square root of 3 is just a constant. So instead, I got to figure out what happens to changes in the line current. That'll tell me what's changing with the three-phase apparent power because there's no change to the line voltage. How do I calculate the line voltage of a three-phase load? What tool do we use down here? What tool? Yeah, single-phase equivalent circuit. Single-phase equivalent circuit requires, it's a model, and it requires one phase of a Y-connected power supply feeding one phase of a Y-connected load. If we have a delta connection somewhere, we have to convert. If you were in circuit analysis class last week, you know this like on the back of your hand, right? We did 6, 7, 8 examples of this. So here's our single phase equivalent circuit for the Y and the delta. What voltage goes right here? This is always what? My line voltage divided by the square root of 3. We can call this the line to neutral voltage to avoid any confusion. What's my impedance? This is going to be one phase of a Y connected impedance. This is this value right here. My impedance is already Y connected first, so whatever the numbers are here, 1 plus J2, 3 plus J5, they go directly in this box. What's the magic of the single phase equivalent circuit? What does this current equal right here? This is the phase current of the single phase equivalent circuit, but the whole point of the single phase equivalent circuit is this current right here is going to equal the line current of the system that I modeled it after. So using Ohm's law, I can calculate my line current of my Y-connected load. Ohm's law is I equals V over Z. I equals V over Z. All right, let's make a equivalent circuit for the delta connection. Any change to the voltage in my single phase equivalent circuit when I model my delta connected load, do I use the phase current of the delta connection or am I using the phase current of the system? The line to neutral voltage of the system. We're still using the line to neutral voltage, even if it's not there. This is just a model on paper to help us simplify analysis. Again, if you attended class 2 last week, you're real comfortable with this relationship. Now, here's what changes. Can I take the same complex Z value that exists from A to B in my delta connection and put it right here in this box in my single phase equivalent circuit? No, says Wayne. What do I got to do? How do I calculate this impedance right here? I got to convert from delta to Y. Single phase equivalent circuit uses one phase of a Y connected power supply, one phase of a Y connected load. If I have a delta anywhere, we got to find the Y equivalence, and we have to use the Y equivalence in our single phase equivalent circuit model, right? This is a model, it's just a tool. It doesn't exist in real life, it just helps us do the math by hand. So how do I convert this balanced delta impedance to one phase of its balanced Y equivalent? Yeah, we divide it by 3. Whatever the delta impedance is, we divide it by 3. This is complex Z divided by 3. This value is the same as this value is the same as this value because we've taken the same three-phase Y-connected load. We've broken it up. So I just have 3 individual single-phase loads. I have 3 individual, whatever this complex impedance value is. And then we've reconnected those 3 individual impedances into a triangle, into a delta connection, according to the problem. So the only thing that changes in my single phase equivalent circuit for this delta connected load is I have to divide the impedance by 3. Now, the phase current in the single phase equivalent circuit, it's going to equal the line current drawn by my delta connected load. That's the whole point of a single phase equivalent circuit. That's what I like to refer to as the magic. All right, so now I can solve for the line current of the delta connected load using Ohm's law with the single phase equivalent circuit, just like we already did for the Y connection. What's going to change in this formula? I still have I equals V over Z. There's no change to V, but now look at the Z value. Now we've got to divide Z by 3. How do I simplify this? That's like what? Can I move that 3? Get away from the page number. Can I move this 3 to the top of the fraction? Look, that's like 3 times our line to neutral voltage divided by 3. Interesting. All right, now I have the relationship for the line current drawn by my delta connected load and the line current drawn by my Y connected load. Let's evaluate these using the three-phase apparent power formula. So for my Y connection, three-phase apparent power equals square root 3 times my line voltage. I'm just going to use VL, right? They're equal in both circuits, times my line current. I'm going to leave that blank for now. For my delta connection, three-phase apparent power equals square root of 3 times the line voltage times the line current, right? Again, no change to the line voltages here. All right, let's plug in the line current. Line current for our Y connection is the line to neutral voltage divided by the impedance. Line current for the delta connection is 3 times the line to neutral voltage divided by the impedance. What's the only difference between these two formulas, between these two expressions? It's the only difference. Anyone spot it? Yeah, the 3, look. There's 3 right here. Square root of 3, square root of 3. Line voltage is the same, line voltage is the same. Line to neutral voltage of the system is the same, line to neutral voltage of the system is the same. The balanced impedance in each phase of the Y connection equals the balanced impedance in each phase of the delta connection. Does everyone see how the delta connected load is going to draw 3 times more apparent power than the apparent power drawn by the Y connected load? Does everyone recognize how that 3 makes all the change? Pretty neat, huh? Now, I took way longer than 6 minutes to solve this, but when you're familiar with this stuff, it's quick. It's real quick. I'm taking our time, we're walking you through it, explaining it, looking at the diagrams, looking at the formulas. When we learn it, we want to take our time, but on the PE exam, man, this is a quick problem if we're familiar with it. So again, this is what I call a quantitative problem disguised as qualitative, right? If the problem said a 1 plus J2 ohm Y-connected load is fed from a 208 volt power supply, what happens if I take that same whatever impedance load, but I delta connected it instead? how much apparent power would be drawn by the delta connection? Well, then I'm just plugging in numbers, right? Well, like we can use the formulas with just the variables without plugging in numbers to see what the changes are. So it's like a quantitative problem with numbers disguised as qualitative. We're still using formulas, we're just not plugging any numbers in. Daniel said participating in class 2 and the pre-coursework really helps. Excellent, Daniel. Excellent. All right. Any questions on this before moving on? That's just number 10. We got two more, at least two more to go. The problem didn't include these diagrams, but it's the same diagrams from that first circuit analysis problem we worked. So yeah, it says from the previous problem, and in the book, this is really question number 2, immediately following the previous one. In the previous problem, we saw the delta connected load draws 3 times more line current, right? That was the answer of the previous problem. So this also results in 3 times more apparent power. An increase in 3 times the line current, which we can see down here. Look, the delta connected load draws 3 times more line current compared to the Y connected load, because look, this is the same, this is the same, this is the same. A 3 times increase in the line current results in a 3-time increase in the apparent power. Bailey said, did you just arbitrarily choose to use the line value 3-phase equation instead of the phase values? No, I didn't. That wasn't arbitrary because the answer choices are all asking about how much apparent power, the difference in apparent power, right? These loads, a Y-connected load and a delta-connected load, those are 3-phase loads. So they're asking about the total 3-phase apparent power. So I'm going to start with, man, they're asking me about any changes in 3-phase apparent power. So I'm going to start by investigating the 3-phase apparent power formula. Square root of 3 is a number. It's just a coefficient. That's not going to change. Line voltage, well, assuming they're still fed from the same system, that's not going to change. So now I got to find a formula for line current. Line current and impedance uses Ohm's law, right? But Ohm's law is a single phase formula, so we got to use the single phase equivalent circuit to solve for it. Okay, here we go. Question number 11, transformers. What scenario below would warrant using an auto transformer instead of a standard power transformer? A, when the primary and secondary circuits require electrical isolation. B, when the voltage supply needs to be adjusted by a small increment. C, when a neutral point for grounding purposes is required in an unground system. Or D, when a filter for power surges in high voltage power systems is required. What do you think? A, B, C, or D? Seeing just about all B's. Good. I see a couple of D's. Is there any of these we can obviously eliminate? What about A? What does electrical isolation mean when we talk about a transformer? If I sketch a one phase of a 3-phase transformer, or just if I sketch a single phase transformer, right? Real quick. Here's a single phase transformer, drawn freehand. Don't judge me too harshly. Not bad though. So here's a normal transformer. Let's draw an auto transformer. Look, we can do it this way. Here's my nice and quick, my auto transformer. What's electrical isolation? Which one of these two has electrical isolation? Which one doesn't? Yeah, Wayne said there's a gap here. There's no connection. Yeah, there is no physical connection on a standard transformer between the primary N1 winding and the secondary N2 winding. There's an air gap. This is what we call electrical isolation. Do I have an air gap on my auto transformer? Here's my common winding. Here's my series winding. I don't, right? Look, these are physically connected. They're electrically connected. The conductors are touching. So would I ever use an auto transformer when I need electrical isolation? No way, right? Auto transformers don't have electrical isolation. It's one of the disadvantages. So they can eliminate A. How about C? Hmm, I'm sure I could put a grounding. I'm sure I could ground a three-phase auto transformer. If I made a neutral here, yeah, I could still ground it. But when I think of system grounding, we're just going to ground the service transformer. I'm not going to have an auto transformer as a service transformer, right? I'm going to eliminate C. D, filter for power surges. Well, I know a lot of times filters use inductors. I mean, a transformer is an inductor, maybe. Maybe leave that one blank. So I've reasonably just dialed this down. This is a 50-50 coin toss, right? This is like who gets to kick, who gets to receive. Coin toss. So the answer is B. The primary application for auto transformers is when we're adjusting the voltage by like 10%. That's all. Since there's no electrical isolation, look, no isolation, right? All of the voltage and current on the secondary side of a regular transformer has to be induced through the flux in the air gap from the primary to the secondary. On an auto transformer, I've got flux induced in my common winding if I'm stepping up, right? That induces a little bit of voltage and current in my series winding, but then I still have some current that's directly flowing through that node. It makes the auto transformers more efficient, right? Current can flow way better through a conductor than it can be induced through an air gap through flux. So your auto transformers, you can build them smaller and they can be more efficient, which makes them way more cost effective compared to a standard power transformer. Because really in an auto transformer, I really only have one winding that I'm essentially just kind of center tapping. So they're cheaper. And the main application of this are minor voltage adjustments. My favorite example, and we talked about this the night before last when we covered auto transformers at the start of day one, class three transformers. Can't believe we're already on the third week of Y class semester. Most common example is if we're really far from the utility generating station, we're out in the country, you're going to see auto transformers as you drive by. Biggest application of auto transformers are on distribution lines, transmission lines to bump up the voltage a little bit to account for the voltage drop going from your nearest utility substation all the way to a really long run out in the country. So what's the disadvantage? Why don't we use auto transformers for service transformers? Well, again, that lack of electrical isolation increases big safety risks, decreases reliability, which. All right, that's auto transformers. Let's see if we can knock out the last one in the last 10 minutes so we can stick to 4 problems. Charles says, wait, is that why the apparent power goes up when you reconfigure? Yeah, exactly, Charles. An auto transformer can supply, if you reconfigure a single, great intuition. If we take a single phase transformer and I put a jumper on it to make it an auto transformer, it can now supply more power as an auto transformer because auto transformers are more efficient. Some of the current and voltage is flowing directly through from primary to secondary instead of having to flow through the air gap and induced through the magnetic flux. Yes, wonderful. Great intuition, Charles. All right, last one. This is very similar to, well, I believe we did this on the week one of qualitative questions. But what information does the design class letter on an induction motor's nameplate primarily represent? And I've got a little itty bitty. Let's see if we can grab this. It's only half a horsepower, but it's still heavy. So design class letter. Here's my fun little, it's still heavy, half horsepower. I think it's like a 208 motor. And this motor says class B. What does class B? It says code M and class B. We talked about what code M means on week one of this webinar. This damn heavy little, oh, it's not half a horsepower. It's 1/12 of a horsepower. Jeez. Only draws half an amp. Half an amp at 120. I thought this was half a horsepower. This is 1/12 of a horsepower. Thing's heavy, man. This is like, this is all like 15, 20 pounds. It's like a little kettlebell. Could do some shoulder presses with this thing. All right, A, class letter, is that motor efficiency? B, is that locked rotor kVA per horsepower? C, is that torque for speed curve characteristics? Or is it the type of insulation? I know it's not what? I know it's not B. We talked about B. B is not class letter or design letter or NEMA letter. This is what? B is the code letter, which lets us look up that table in the NEC. That'll let you know how much kVA per horsepower happens when the motor is either started from rest or when it locks up, locked rotor. All right, I'm looking in the chat. Uh-oh, some of you said B. Michael, are you not here for week one? Great. Yeah, I'm seeing just about all C's. Excellent. So it's not motor efficiency. Let me see. This is such a small motor, the efficiency is crap. This is a 1725 RPM, so we could use that to find the slip. This is 1.4 service factor, single phase. NEMA, nominal efficiency. This motor efficiency is only 44%. That's garbage. Smaller the motor, the worse the efficiency. So it's not efficiency. I can't believe the power factor on this thing's only 52.52. That's almost hard to believe. I'm used to the I'm used to medium voltage motors or low voltage at 480. I mean, for me, a small motor is at least 25 horse or 50 horse. Even those are going to be on at least around the 80% power factor and mid 80s or 90s efficiency. So it's not the efficiency. It's also not the insulation type. Usually they'll indicate the insulation. I should have taken a picture of this nameplate. So this one, you'd have to look up in the catalog number to see the insulation. Usually I know F insulation is the most common. You'll see like insulation F. That's typically the most common insulation type, and I believe that's the type of insulation you can use for VFDs. But yeah, everybody that said C, this is the speed versus torque characteristic. I'm going to try to snap a picture of this motor and pull it up on the screen real quick. So this is what? This is our NEMA designation. NEMA B, C, D, E, F motor. All this letter tells us is we can look up that class designation in a NEMA catalog or anywhere, and it's going to give us the torque. There we go. Not bad. It's going to give us the torque versus speed characteristics. Here's the locked rotor torque or the starting torque. Here's the pull-up torque. Here's the point of breakdown. We could say that's probably rated. You could say this is 100% torque. This is our rated speed. This would be synchronous speed. Never gets to that point. This is breakdown speed or maximum torque momentarily when the motor reaches breakdown and continues. All right, any questions? Let's see if we can stick this nameplate in the chat. It'd be fun. See if I can do this quickly. Got a little bit of a reflection there, but not bad. Gotta love Mac computers. Let's airdrop this bad boy. All right, you guys ready to check out this? Can everybody see that okay? I just pulled it up on my screen. Should be covering up like half the screen. Everybody see the nameplate? Great. Yeah, so let's check it out. Catalog number. This just lets us look up in the manufacturer. It lets us look up the exact motor data, right? I want to order this exact motor. That's the catalog number. The spec number, I'm not too sure about that. Maybe that's like a serial. Yeah, look how tiny this is. Just half, not half, 1/12 of a horsepower. It's cut off here, but that's volts. This is a dual voltage rated motor. We can operate at 115 or 230, fed by a 120 or 240 volt power supply, right? The difference just allows for voltage drop by the time it gets to your motor. Amps, again, that's cut off. I took the picture quickly. My apologies. Amps is half an amp, so 0.5 amps. Look, here's the RPM, 1725. Could I figure out the number of poles in this motor and then figure out the slip at rated conditions? Yeah, sure could, right? Look, synchronous speed equals 120 times frequency over P number of poles. If we divide by the rated speed, we can estimate the number of poles. This is a 4-pole motor. This is a This is an 1800 RPM synchronous speed motor with a rated motor speed of 1725 RPMs. That's how fast it actually spins. We could also use that information, NS minus N over NS, to calculate the slip. Here's the frame. Anyone know what the frame means? The frame is the mounting frame. Motor frames were the bane of my existence when I worked in an electrical plant. Massive motor burns up in the middle of the night. You get called, you get woken up to go replace it. You got to figure out, well, I've got the same voltage, the same current, the same horsepower, the same speed. So it spins the pump or the conveyor or the elevator at the same speed. You check it out, you wake everybody up, you check it out of the warehouse, you get a crane, you get a forklift operator to wake up, go pull it out of the warehouse. You wake up a crane operator to come pick it up. You wake up the maintenance crew to come uncouple the old motor, pull it off with a crane, and now we land it. But guess what? You did all that work. It's been 6 hours by now. The sun's coming up, and this base, this frame doesn't fit. Frame's a pain in the butt when you deal with big motors. Look, 60 hertz, one phase. Here's our service factor, so it can operate 40% above rated conditions. Code M, we could look up the kVA per horsepower in the National Electrical Code for a Code M motor of the locked rotor. Designation dash, I'm not too sure about that. Class B, here's our NEMA. This is a NEMA B motor, most common type of motor for general purpose. Look at this. I'm shocked by this, even for a small motor. Nominal efficiency, 44%. What does that tell us? A lot of power losses, a lot of heat. Power factor, 52%. Shocked by that. What does that tell us? This motor is going to draw a lot of reactive power. This is cut off, but that says the rating. Oh, okay. This is 40C ambient continuous. 40C is your ambient rated temperature for National Electrical Code sizing purposes, ambient temperature, which is standard, and continuous duty. So I'd have to multiply by 125% if I'm sizing the conductors. Continuous duty means I can run this motor for as long as I want, more than 3 hours. CC, I'm not sure, but that's blank. Look, it says usable at 208. Look at that. So if I run it at 208 single phase instead of 120 or 240, it's going to draw more amps, 1.15. Bearing designation 6203. I'd never rewind a motor this small. I'm just going to throw it out. ODE, I got no clue what that is. Enclosure, TEFC. I forget what that stands for. But I believe that's the squirrel cage specific enclosure. TEFC is the most common. I think it's like flame something, or I forget. Anyone know what TEFC is? Serial number. This is the exact serial number of this specific motor I'm holding in my hands. Thank you, Bailey and Yalda. TEFC, totally enclosed forced cooling. Great. Yeah, it's totally enclosed. Look at this, forced cooling. See those slots? I don't know if you can see it. I'm so scared to drop this thing. I'm telling you, this thing's freaking heavy. Look, I'm going to spin the rotor. You guys see the fan spinning? See the fan? I'm so scared I'm gonna drop this. It's so small, but it's so heavy. I might have to work out with this in my garage when we're done. The rotor, there is a fan in the back coupled to it. So as the motor spins, it draws either air in or pushes it out. I can't remember, but it helps to cool down the motor windings. And then the last is SFA 2.2/1.1. I'm not sure what that is. SF makes me think of service factor, but we already have this service factor right here, SCRF 1.4. So I'm not sure what that is. They can ask you a ton of questions on motor nameplates as well. Cool. You guys like that? We're just about at the end of the hour. Any questions before we get going? Any questions before we get going? Michael said the NEC is the electrical code letter. Yep. And the NEMA is the Manufacturers Association design letter. Yeah. Any questions? Sarah said is a reg and auto trans. Sarah, I'm not sure what you mean by that. If you could clarify, happy to answer. Daniel said, thank you. You are so awesome, master. Keep it work. Hey, happy to help. You can use auto transformers are used for voltage regulation. Yes, voltage regulation after a long drop on a transmission line, like that example we talked about, we can regulate the voltage. We can bump it up to our nominal rating as close as possible. Stick an auto transformer at the end of the run. When is the seminar for Ohm Gurus available? Next week we're doing SCADA systems. I'll be next week. This is not Ohm Gurus. This is qualitative questions for the PE exam, but this recording will be on our YouTube channel as well. All right, any last minute questions before we get going? Has anyone here bought the physical copy of the Master in the PE exam, 100 qualitative practice problems for the electrical power PE exam? This is just my proof copy. You can see right here when we were proofreading the final copy of it. I got about 20 author copies that should be here Sunday. I'll probably do a big giveaway on LinkedIn or Reddit or something. Good. I see a lot of you with the physical copy. Yeah, it's a beautiful book, if I may say so myself. It's awesome. Nothing beats having it in your hand. You can take it anywhere, take it on an airplane, road trip. It's formatted really well. We spent a lot of time on this. This was almost about 2 full years, full of diagrams. The reference handbook is referenced at every point where you can find all these diagrams. Got phasor diagrams. The protection is the biggest section on the P exam. I'm really proud of these protection questions. I haven't seen protection questions like this anywhere else. And I drew from a lot of real world experience, especially this CT polarity question. I drew in a lot of real world experience of what I've encountered troubleshooting in the field with my hard hat, with my meter, with my flame retardant clothing, with my boots. And a lot of that stuff is what they're going to ask you on. And the neat thing is all of these questions that are real world experience questions, we can tie them into formulas and fundamentals. So even if you've never encountered this stuff in the field, you can kind of think through them using what we teach during the class, of course, as a way to kind of piece it together like a puzzle to figure out what they're asking for, even if you've never encountered it, right? You can eliminate obvious answers and then using the fundamentals, using the formulas, using what you've learned in each subject, you can come to a really good educated guess. All right, any last minute questions before we go? Everybody like the seminar series? I will be doing, once these end, I'm going to be doing private sessions again with students with our enrolled students. If you're in live class, then you know about those. And I'm probably going to do those live too and invite anyone that wants to sit in. That way we can all learn from these discussions. And I'll probably be posting those on our YouTube channel too. So, all right, everybody. Next week, we will be having the last webinar of this series on January 30th, 2025. If you've already registered, if you're already here, it was the same registration page for all four. So you should be able to use the same link and you should automatically get that email reminder. All right, everybody, thank you so much for joining. Hope you enjoyed it. I certainly did. And I will see everybody next week for our last webinar in this series. See you then.